Hello, calculus students. Today we're going to begin a new topic called where we're finding the volume of a solid. And we're going to do this in a couple different ways. And the first way we're going to do it is by revolution or rotation. And we're going to first look at what are called the disk and washer methods for finding volume. And we're going to be rotating first about horizontal line. Okay, so what is this all about? So what's happening here is you're going to be starting with a cross-sectional area. Okay, so you can see here we have our region bounded by the line y equals x from x equals 0 to x equals 4. And now you guys would know how to find the area of this triangle by doing an integral. But what we're going to do is we're going to do volume by rotating this about the x-axis. So I'm going to show you a visual for that. So just bear with me for a second so we can pull it up. All right, so this is what I'm talking about. So what you can see here is we have our triangle, and you can see that this is the triangular region that I just showed you. And what we're doing is we're taking that triangle and we're pivoting or rotating it in front of the x-axis and behind the x-axis. So you do see a third axis on here, but we don't need that, okay, because everything is based off of this triangular shape. Okay, and in this case, you can see, imagine this is being filled up as it rotates around. And what the shape that it's creating is a cone. Now, of course, this one creates a perfect geometric shape because your function was a straight line. But, you know, try and imagine now in your head, like if this was like a parabola shape or a sine curve or something like that, instead of just a straight line, you would get a very different and unique shape for the volume that you are creating. Okay, so what happens here is, and I'm going to go out to a different animation now, so hold on. So what happens here is we're going to create cross sections, okay, to find our volume. Okay, so if you see here, what happens is I want you to think about this as a Riemann sum. So this is what's called a cylindrical cross section. So you can see that this is a very thin little cylinder where your radius is defined from your x-axis to your function, which in this case is the line y equals x. And you can see that the width of your cylinder is very thin. So imagine, like, as I move through here, you can see that I create cylinders of all different sizes, very small down here where the function is really close to the x-axis. And then it gets larger and larger as it gets closer or gets further away from the x-axis because your function is growing. But when you look at each individual slice, okay, so what happens here is when you're looking at this, you can see that the volume, or the radius of this cylindrical disc, again, is based off the length from the function to the x-axis right here, which is just your y value. And remember, y is always your function. And again, the width is very thin. So we're just going to basically be finding the volume of all of these little cylinders as we move across the function, and we're going to be adding them up, which of course is a Riemann sum. And if you put in an infinite number of cylinders in here, okay, then that is going to create an integral. So your integral is going to be based off of a Riemann sum of the volume of a whole bunch of tiny little super thin cylinders. Okay, so now I'm going to go back to my PowerPoint. All right, and okay, we already saw that. So now let's look at this just let's get all of these things that we were talking about. Let's get it all together. Okay, so the first thing is if you're finding the volume of a cylindrical disc, the first thing that you need is the formula for the volume of a cylinder. And maybe you know it, but if you don't, here it is. The formula for the volume of any cylinder is pi times the radius squared times the height. So remember, in this case, we were saying that the radius of each cylindrical disc is based from the x-axis to your function, which is f of x. So what I'm going to do is I'm going to come over here to my volume formula, and I'm going to replace r with f of x, our function. And then the height of each cylinder is that tiny little sliver of a height, which if you remember when we did Riemann sums, we called the width of each interval delta x. So rewriting the volume formula with, we still have our pi, then we have our function squared, and then we have our width, which we always refer to as delta x. So you remember as your number of cylinders or partitions approaches infinity, this becomes an integral. Okay, so that means putting this all together is when we add up the area of each cross section, it is a Riemann sum of your volume. So you get the following formula. So the integral from point A to point B, which are your left and right boundaries as usual, times pi times f of x squared dx. Now, normally what I do is I bring the pi out in the front of my integral, and so that if I'm integrating without my calculator, I can just multiply it through at the end and I don't have to worry about it. If you have your calculator, it doesn't matter which way you do it. Remember, any decimal approximation is perfectly fine as long as you're using at least 3 or 4 decimal places. All right, so what was unique about this particular formula, what's unique about it is that the radius of the cylinder, okay, is always defined from your line of rotation. In this case, the radius and your function are the same because our line of rotation was the x-axis. But as we progress through this unit, you're going to see that the x-axis is not always going to be your line of rotation. So a general formula for rotating about a horizontal line using the disk method is the integral from a to b, your x equals a to x equals b, your left and right boundaries, times pi times the radius of each cylindrical disc squared. Again, the only time it will be the exact function, the only time this will be f of x, is if you're rotating about the x-axis. As soon as you change your line of rotation, this length will change, okay? And we'll hit those later on this week. All right, so today we're only going to do x-axis rotation, so our radius is always going to be f of x for the most part, as long as you're using the disk method. All right, so I already said that. All right, so let's actually find the volume of this shape, which we saw is going to create a cone. So let's find the volume of the cone using an integral. So again, the basic setup for the word problem will be you're finding volume. It has to give you all of your lines, your boundaries. Okay, so we were given y equals x, the x-axis as a boundary, and limits from x equals 0 to x equals 4. And of course, 4 was not, you basically have to enclose your shape. Okay, so if you don't have it, then just drop a vertical line. They also have to tell you your line of rotation. So again, this is going to be a disk method, okay, where you follow the general formula that I gave you, because when you look at your shaded region, the x-axis is a boundary. Okay, so it's disk because your x-axis is a boundary. Okay, and you're also rotating about the x-axis. So when you're rotating about the x-axis and the x-axis is a boundary, okay, it is the disk method. All right, so that means we just have to put everything into the formula that I gave you. So we know that our basic formula is v equals a to b pi times the radius squared. In this example, our radius is the exact function itself, and the function in this case, f of x, is just equal to x. So we're going to substitute x in for our radius. And our interval was from x equals 0 to x equals 4, and then pi times x squared. All right, so this one is very easy to do without a calculator, so we'll just do that really quickly. So the antiderivative of x squared is 1/3 x cubed, and then you're going to substitute in 4 and 0. 4 cubed is 64, and then of course at 0 it is 0. So you end up with 64/3 pi cubic units, whatever they happen to be for volume. Usually we don't really talk about the units, but if they were, there would be cubed. All right, let's do another example. Okay, so example 2, we want to find the volume of the solid formed by rotating the region bounded by y equals x squared and the x-axis about the x-axis. And again, the x-axis is a boundary. You're rotating about the x-axis, which means you're using your basic disk method formula. Okay, so you should all know what y equals x squared looks like. A basic parabola with its vertex at the origin. And the x-axis, so again, your boundary lines, function, x-axis, and then we drop a vertical line down for left-hand or right-hand limit. And again, when you look, there's no space here. Okay, so if we made a cylindrical disc going around, this would be the radius of our cylinder. And again, this length defined from the x-axis is always f of x, the function. And I keep harping on these things, and these ones right now are really easy, but try and pay attention to the language I'm using, because as we change our lines of rotation, this is going to become a little bit more difficult and more important of a process. So right here, function, it's also the radius. Okay, so we're going to substitute that into our integral. So again, I just pulled my pi out. So we have pi from 0 to 1, x squared squared, function squared. And of course, x squared squared is x to the 4th. And then very simple antiderivative by the power rule, 1/5 x to the 5th. Substitute in 1 and 0, and you get 1/5 pi, or pi divided by 5, or 0.2 pi, don't care how you write it. And if you want to multiply your pi through, you can, but just make sure you keep 3 or 4 decimal places. All right, so that's the disk method. All right, so now we're going to look at the washer method, and the washer method is pretty much the same as the disk method. It just involves a second function. So it is to be used when the cross-sectional area, like your flat section, is not bounded by the line of rotation. So right now we are rotating about the x-axis. So we're going to be taking two functions and subtracting them. Notice each one is squared. And so it's still the same formula. Like if you took this out, okay, that would be the volume between the further function and the x-axis. And I'll draw a diagram for this as well. And then the second one, you're subtracting out the one that is closer. So the washer method creates a hole. And the reason it's called the washer method is because it's like, you know what a little washer is on a bolt that you put on a bolt to make them stay in. So it's a little ring with a little hole. So it's not a complete cylinder. There's a little section that's subtracted out. So this is the scenario that you would have here, this basic, and we will actually integrate this function. But you have two functions here, a downward facing parabola and an upward facing parabola. So if I call this function f of x and I call this one g of x, okay, when you're looking at how you are going to find the volume rotated about the x-axis, here is your x-axis. This region between them is not bounded by the x-axis. So the x-axis, it does touch the x-axis, and that's okay, but it is not bounded by it. You can see that you have this little space right here between your x-axis and the bottom function, the function that forms the bottom part of your region. And this right here is function g. So this length is g of x. And then if you started and you went all the way up to the top of the region, okay, this length from the x-axis to the curve is function f of x. Okay, so lost my pen. All right, so that's f of x. All right, so basically what you're doing is you're finding the area or the volume if you rotated a whole function f of x around, and then you're going to subtract out what you would get if you rotated function g around, and that will give you the volume of the remaining piece. So this one kind of, I don't know, it looks like almost like a donut, but it doesn't have an actual hole in the middle. It's like one of those donuts where they just kind of come together in the middle. All right, so this is how you apply the washer method. And of course, if you're not rotating about the x-axis, then you're going to be looking at a more generalized formula where you have your pi from x equals a to x equals b. And then we have what's called big R and little r. And big R is the length from the line of rotation to the farthest edge, and R is the length from the line of rotation to the near edge. And again, when you're looking at this formula, the important concept here is that your radius is always from your line of rotation. Length from the line of rotation to the near edge, whichever edge is closer. Okay, but we don't have to worry about that one right now because we're only rotating about the x-axis. So let's get to it. All right, so this was the functions that we were just looking at. And we want to rotate the region that is bounded by y equals 8 minus x squared and y equals x squared from -2 to +2 about the x-axis. Now in this problem, they did not have to give you this. You could always find you're looking for the intersection points, which you can find by setting the two equations equal to each other or using your intersection key on your calculator. But again, those are your left and right edges. Okay, and like I was saying, you're going to take your function that's further from the x-axis, which is your line of rotation, and subtract out the closer one. And again, remember, you're using the washer, okay, because the line of rotation, which in this case is the x-axis, does not form a boundary for your region. The boundaries for the region are this upper curve and this lower curve, and that is it. Okay, no x-axis. So this one I would expect you to integrate with your calculator, but remember this right here, if you're not using your calculator, you have to FOIL that out. Okay, FOIL it out. Okay, don't just square the 8 and square the x squared. Okay, it's a binomial squared. Make sure you FOIL it. And if this was something else besides an x squared, again, the whole function squared is subtracted. So if you were working, like if these two were switched, make sure that after you FOIL it out, that you distribute your negative through the parentheses. And those are just basic algebra skills. Okay, so if you integrate this, go to your calculator, integrate that, you get 170.67 pi. I should really have an extra decimal place there. You can multiply your pi through. It's possible on your 89s, this comes out as a fraction. Okay, so whatever works for you. All right, let's do another one of these. Okay, so this one, you're going to find the volume of the solid obtained by rotating about the x-axis, the region bounded by the graphs of f of x equals x to the 1/2, or the square root of x, and g of x equals x squared. So I already have this drawing done for you here, but I do recommend at this point that you do graph both of these on your calculator, or you can graph them by hand. You should know what the square root of x looks like and x squared. So graph both of those functions. And you're going to see this is a really teeny tiny little cross-sectional area in here. It's just this tiny little space. It is difficult to see the region bounded by these two on your calculator, which is why I want you to look at them together. And of course, you can get the intersection points for these using your calculator or by taking your two equations and setting them equal to each other. And the key now is that you have to see is which function is further from your line of rotation. So again, we're rotating about the x-axis, and you're looking at this is your entire region. Okay, so if you start at your x-axis and go to the outer edge, this is your square root function. And if you start at the x-axis, the line of rotation, and go to the near edge, that is your parabola. Okay, so setting up your integral, you have your pi. Your limits, your intersection points were from 0 to 1. So you're going to have the square root function squared minus the parabola squared. And of course, this is just x, and this is x to the 4th. So a little bit easier to type it in your calculator if you simplify it, but you don't have to. And then just integrate it. You can do the antiderivative by hand, 1/2 x squared minus 1/5 x to the 5th, or just use your integration key and you'll get 3/10 pi or 0.3 pi, or again, you can multiply your pi through. That's up to you. Okay, so we'll do one more example and then we'll be done. Okay, so I want you to find the volume of the solid obtained by revolving about the x-axis, the region bounded by the curves y equals sine of x and y equals cosine of x from 0 to 2 pi. So again, you should be able to graph these right now on your own, looking at them on the calculator. So, you know, do that first and then see if you get the same thing that I got, and shade where you think this region is. So again, look at your limits. You're rotating about the x-axis. That has nothing to do with one of your boundaries. The boundaries have to be the sine curve, the cosine curve, and you are not going past 0 or pi over 2. Okay, so graph it out yourself, and then hopefully this is what you got for your shaded area. Okay, so again, boundary, cosine curve, sine curve, x equals 0, x equals pi divided by 2. Okay, so this one actually splits into 2 sections. Okay, you have from 0 to this point of intersection, and then this point of intersection to pi over 2. All right, now you shouldn't have to use your calculator to get the intersection point. Basically, this is asking you where is the sine function equal to the cosine function. And of course, that is in a 45, 45, 90 triangle when your opposite and adjacent sides are the same. So this is pi over 4. And when you look from 0 to pi over 4, your cosine function is further from the x-axis, your line of rotation, and the sine function forms the lower boundary. And then after you hit pi over 4, they reverse. So the sine function is further, the cosine function is closer. So that means you have to do 2 separate integrals. So the first one, you're going to set it up cosine squared minus sine squared. And the second part from pi over 4 to pi over 2, sine squared minus cosine squared. Okay, so 0 to pi over 4. Again, don't forget your pi out in the front. And you have to use your integration keys for these because you don't know the antiderivative of cosine squared or sine squared. And this is not a Pythagorean identity. So you do, because it's minus, not plus. So you would have to do both of these separately. And each of these sections would give you pi divided by 2 or half pi. So when you take your half pi plus your half pi, and please try this on your calculator so that you make sure you're typing it in correctly. And then you're going to add those 2 volumes together, which will give you pi. Now, just to compare this, what we did with area, okay, when we had area and it went under the x-axis, we had to make it positive. For volume by the disk or washer method, it should always come out positive if you set it up the correct way. Furthest from your line of rotation squared minus closest to the line of rotation squared. If you set it up that way, you should always get a positive answer, okay? Never a negative. Okay, so, and again, you're squaring your functions. You square something, it'll produce a positive, so as long as you have the bigger section first, okay, you'll get it right. So don't worry about the relationship between the curve and the x-axis. Worry about how it is related to your line of rotation. And if you have more than one function, worry about how they are related to each other. Okay, so that's the disk and washer methods. And that is the end of the lesson for today. Okay, so I want you guys, if you have any questions, of course, send me a message. But if not, you have an assignment to work on tomorrow, and have a great day.